I will. But you also need to get better at figuring out on your own. Okay, so Newton's laws, the start of dynamics. Before we begin, well, that's why I should talk about this, right? So a force is a physical quantity that can affect the motion of an object. Can affect the motion of an object. Does a force always cause motion?
No.
No.
But push on that.
Oh yeah, pushing the filing cabinet, no motion, right? So a force isn't always necessarily going to cause motion. It has a magnitude, direction, and a point of application, therefore it is a vector quantity. Out of all that, what do you need to know? Forces are vectors. That's all you need, really, right? Isaac Newton was the first person to clearly describe the relationship between force, mass, and motion. Newton's laws of motion not only apply on Earth, but are true throughout the universe. In other words, we call them universal. Now, there are some situations where Newton's laws don't necessarily apply. Some special situations, and I won't get into it too much, but they are generally universal throughout the universe. If I push on filing cabinets on Pluto, filing cabinets push back on me. It doesn't matter where you are. Okay? Sure. Okay? All right. Now, yesterday we dealt with the fundamental forces. Who can tell me the easiest one to remember? Gravity. Strong nuclear force. Weak nuclear force. Electromagnetic. So you were listening. That's good. Okay. These are not the fundamental ones. These are ones that are based on those four. These are just sort of common, everyday ones that you might need to be aware of. Number one, buoyant force. The buoyant force is produced by fluids. Fluids also include gases, by the way. Tristan, you should listen. If you're not going to write, then you do need to listen. When I say you don't need to write, I don't mean you don't have to listen. That's not enough. Okay? And the fluid force, most of the time, acts upward, we'll say. There might be some occasions where it might not. Maybe. Definitely got still part. Okay, buoyant force. Elastic force. Like if I take the elastic band off my deck of cards here and I stretch it, right? Or I take a spring out of a pen and compress it, or I twist something, Kish's arm, there's an elastic force. Elastic force would probably be based on electromagnetic force, right? Because the molecules are trying to stay together. I'm not sure what the buoyant force would be. Probably electromagnetic. I think so. Electrical force produced by the interaction between charged particles. You remember that whole thing about positive and negatives attracted to each other, and positives not attracted to each other, and all that stuff, electrical force. You know what? This friction force really sort of, rubs me the wrong way. Aren't I really just a game show host here, really? Just without good prizes?
Yeah.
Friction force is produced when one surface moves over another, and it always acts in a direction resisting motion. Does there have to be motion for there to be friction?
No.
Does there have to be motion for there to be friction?
No.
Did you speak too soon, Matthew?
Maybe.
Can you give me an example where there is friction but no motion then?
Something has friction is greater than the force being applied.
Like, paint me a picture. Tell me,
I'm pushing right now. There's still friction,
but not moving, right? He's pushing on his binder lightly. Push on the filing cabinet. Friction, right? Also, good point, then. Push on the filing cabinet. Too much friction, filing cabinet doesn't move. Filing cabinet pushes on me. Too much friction on me. Right? If I turn my feet like this and put on rollerblades and I push, what's going to happen?
You're going to go.
I will go backwards because I've got much less friction. So yes, there does not need to be motion for there to be friction. But friction always acts opposite to the motion or the intended motion, or the direction of the attempted motion, we'll say. Okay. Gravitational force produced between the start again. Produced by the attraction of any two objects. Okay, we had the discussion the other day about me being attracted to the filing cabinet. Right, due to gravity. Is the filing cabinet attracted to me too?
Yeah.
Because it's just a filing cabinet.
Really? Is that attracted to me? I've heard it. Newton said it should be. Right?
It works that the way that when you like say roll a marble by something big, it doesn't get sucked into it.
Well, the force of gravity is really quite small then. And I'm going to go a little bit ahead here, but you don't need to write this down. The actual Newton's law actually says, he has a gravitational law. It's big G times M1 times M2 all over the R squared. And the M1 and the M2 stand for mass. Mass of a marble is pretty tiny, right? How big are we talking about your second thing here?
Let's say a truck.
A truck, okay. Generally pretty small in the gravitational sense, right? The radius is in meters, but big G right here, this is a constant. It's 6.67 times 10 to the minus 31. 0.00000, 30 zeros, right? So anything times that is going to be pretty small, so the actual F value is like incredibly small. You need something on the scale of like a moon to have a... Do you have a gravitational field? Absolutely. It's just not very strong. Trucks have a gravitational field? Again, not big enough. We mean, like when we say big, we mean big, you know? Big.
Like sun.
Like, yeah, like planetary, like asteroids. Asteroids would have like just a tiny little bit of gravity, right? Magnetic force produced by the interaction of at least one magnet and another object. Like, so for example, like, like a fridge magnet kind of thing, right? There's a magnet there. The fridge isn't magnetic. It's metallic, of course. Can two magnets attract each other?
Yeah.
I can't remember.
Can two magnets attract each other? Absolutely. When you say positive, what's the polarity of magnets? Like it's not positive, negative, right? What is it? North and south, right? When if it's one north and one south, they'll attract. If it's north and north, they don't like that, right? Okay, so again, these are all just different common types of forces. You just need to be aware of them. Any force that I give you is just going to be one of them. It's really not that big of a deal. Is there one more there? There isn't. Just 6? Okay. Let's talk about Newton's first law of motion. Here's my version. Most of the time, if I said to you, an object at rest will, an object in motion will. Okay, most people know that. Okay. The second part of that is should be expanded upon for grade levels. If there's no force acting on a body, it will continue in its state of rest or will continue moving along a straight line with uniform speed. You really need that. If you're going to finish that sentence, an object at rest will stay at rest, an object in motion will stay in motion at a constant speed and in a straight line. What does that mean? I'll get out my tennis ball. If I put the tennis ball in motion and I fire it at Tristan's head, once it leaves my hand, it should do what? Continue in a straight line at a constant speed. Does it continue in a straight line?
No.
Because of
Gravity.
gravity. Right? So, if that only is true if there is no force acting on a body. But there is, as Ben points out, there is gravity. If we could somehow go to a gravitational free space, this ball would go straight line. It would look really weird for us, right?
Mm-hmm.
It would look really weird. Now, when I say there is no force, what if there's more than one force?
Magnetic and gravitational?
Okay, what if there's gravity? What if I've got some crazy super villain room, an anti-gravity generator on top? Could I make the ball go in a straight line? Because that's my goal.
Maybe.
Sure, right? But there's two forces acting on it. So what I really mean when I say no force, what I really mean is the net force is equal to
0.
That's really what I mean. What do I mean by the net force?
Overall.
Yeah, overall, sum of all the forces, the total value of all the forces. That's really what I mean. Okay? If there's no force, if the net force is 0, it will continue in its state of rest or will continue moving along a straight line with uniform speed, the same speed. Good. This is known as the law of inertia, the law of teenagers. Things like doing what, actually it's the law of people, right?
Yeah.
People like doing what they're already doing. Yeah, people don't like change.
Which is true.
Although I like,
Unless I'm doing homework, then I don't mind change.
oh, good point, yeah. Homework, the great.
Oh, you like change?
Thanks, Connor. All right, my friends, I'm going to give you about 30 seconds, and then I'm going to make you answer.
Otherwise, not going north.
Nowhere.
That's magnet. Yeah.
Oh.
I'm going to ask you yes or no.
Maybe.
We don't have to explain, just say yes or no, right? Hands up, yes or no. Okay, I haven't given the question yet, Matthew. You can't answer. How many people say yes, that object is moving? You're a brave man, Kish. Good for you. Anybody want to join him on the yes island?
No, I'm not that stupid.
Logan? Okay. Who says no, it's not moving? I didn't see your hand up, Sam. Gage, I didn't see your hand up. Okay, I'm going to give you another chance. Yes? Matthew and Logan? Anybody else want to say yes? Yes, it's moving? Gage is going to join you.
Yay.
Nice. No, not moving, Mr. Bennett.
Switching my vote, yes.
Are you? Well, I got news for all of you. You're all wrong.
Yay.
You're all wrong. How can you all be wrong?
Mr. Bennett's wrong too. We could have
I didn't put my hand up.
So what are you saying, Gage?
I didn't put my hand up once. I didn't.
How can it not be yes or no? Because the answer is maybe.
That's why I didn't put my hand up.
That's why so many questions.
The answer is actually, it depends on what it was doing before. You can't tell from that picture, because if the object was already not moving, me and the filing cabinet, 50-50, not moving. But if the filing cabinet is already moving, and I'm pushing with 50,
It's pushing a 50.
friction is pushing back on me with 50, then that means the filing cabinet is moving at a constant speed. Okay? What it really means is if the object is moving, what it really means is that the acceleration is 0. And if the acceleration is 0, that means it's either at rest or it's moving at a constant speed. I'm going to ask you that question several more times in the next 2.5 weeks. A variety of different ways. Your job is to figure out what I'm asking.
Except will you make sure that it's either moving or not moving?
What else could it be doing?
Maybe.
So it'll always be maybe every time.
I won't ask it that way every time, though. I will disguise it.
But the answer's always
we won't know.
Well, no, it depends on how I word the question. Because I might ask you, how much force do you need to keep it moving, or, I'll be testing for understanding, so. Depending on whether it's moving or not. All right, okay. This one is long, right?
I don't like this one.
No, I know. Where's my little thingy? My little, where is it?
Highlighter?
No, I don't want the highlighter. I want this shade thing. There we go. Let's go with that. So, Newton's second law of motion says the effect of an applied force, this is the one that Howard read, the effect of an applied force is to cause the body to accelerate in the direction of the force. The acceleration is in direct proportion to the force and in inverse proportion to the mass of the body. I'll give you 30 seconds to write it down, then I'll explain. So, the effect of an applied force is to cause the body to accelerate in the direction of the force. In other words, Katie, the applied force will and the acceleration are in the, Katie, the force and the acceleration are in the same, starts with a D, direction. The acceleration is in direct proportion to the force. In other words, big force means big acceleration. Inverse proportion means big mass, small acceleration. Okay, that's what that means. In other words, the more force, the more acceleration, Connor, and the more mass, the less acceleration. And the mathematicians like to write it like this. Now, what the heck is
The fish.
the fish thing?
Broken.
No, it's actually a Greek letter. I think it's, is it gamma? I don't know. I can't remember which Greek letter it is, but it's a Greek letter. No, I don't speak Greek. I know most of the alphabet though. It looks like that. It's kind of a fish thing. Is what kids call it. It means proportional to. Okay. So what this means is that the acceleration is proportional to the force over the mass. The acceleration is proportional to the force. The bigger the force, the bigger the acceleration. The bigger the mass, it's
Smaller.
It's smaller because it's an inverse. It's on the bottom, right? Like if I've got like 1/2 and 1/10, when the number on the bottom gets bigger, then the value of the whole thing gets smaller. So it's an inverse proportion. Inverse proportion. Excuse me. Now, if a force is applied to a body at rest, the body will begin to move. If a textbook is sitting on a table and I give it a push, hey, it moves, right?
That's not always. What?
Yeah, you're right. There has to be, we maybe should change that so it says if a net force is applied, right? It has to be more than friction. If a net force is applied to a body at rest, the body will begin to move. If the body is moving in a straight line and a force is applied in the direction of motion, the body will accelerate. In other words, if it's already moving and I give it a push in the direction that it's moving, then it will go faster. Miguel, you need to let her listen, okay? And if the force is applied in a direction that's not in line with the motion, then the acceleration will be in the direction of the force. Remember the tennis ball going to Tristan, right? Which direction was the force? Down, and so the acceleration is down and it makes it curve.
I'm only still in this class because you're concept.
So if you rework that proportionality statement, you get this equation, F equals ma, right? And that's the formula that many of you have used in grade 10. F equals ma, the F is for?
Newtons.
It's the force, right? F is force, m is mass,
Kilograms.
a is acceleration, right? The force is measured in newtons, the m is measured in kilograms, and the acceleration is measured in meters per second squared. Now, if you combine the units for mass and acceleration, you get a kilogram meter per second squared. That is defined as 1 Newton. 1 Newton is the amount of force needed to accelerate a 1 kilogram mass at 1 meter per second squared. How big is a Newton? Like if I came over and smacked Matt in the head with a Newton of force, would it hurt much?
No.
Not really. 1 Newton of force is about the amount of force I'm applying to this tennis ball to hold it in the air. Roughly. Okay, it's not that much. It's not that much, yeah. A Newton of force is not that much. Okay? Sometimes units of force, especially in America, are measured in pounds. Pound of force. Okay? Your weight in pounds is actually a measure of force. It's not really a measure of mass. So if you weigh 165 pounds, it's how much force you are applying to the ground.
Is that usually gravity?
Yeah, that's because of gravity. It doesn't include it, it's because of.
So is that why you're lighter on the moon?
Yeah. Okay, Newton's third law says when one body exerts a force on another, the second body exerts on the first a force of equal magnitude in the opposite direction. Those are the two words when I'm asking for something like that on a test that I'm going to look for. Equal and opposite. They must be equal. Some people think, right, that when I'm pushing on the filing cabinet, right, and it doesn't move, then it's equal. But if I push hard enough to make the filing cabinet move, well, then I'm pushing harder on it than it's pushing on me. Wrong. It pushes as much as I want. 10,000 newtons of force, and I can come up with it. Pushes on me with 10,000 newtons of force.
Basically means you're going to move back.
Can't avoid it. Can't avoid it. Okay? That's a good point. Bo is concerned because now what he's saying is, well, the net force is 0, right? The net force on the two of us is 0. But what's the force just on the filing cabinet? 10,000 newtons. It doesn't care what the force on me, right? The force on it is 10,000 newtons. It knows, oh, I got to move. Okay? The net force on it is 10,000. The net force on the system, the two of us, is at 0.
Well then, what happens if you do the same thing to a vehicle?
Explain more.
I don't know, I'm just
You're trying to mess me up.
Yeah.
Yeah.
Walk out, good.
Not even close to that.
You ran.
This occurs all time in nature. There's always an action force and a reaction force. Okay, so for example, textbook sitting here has a weight of about, 5 newtons or so. Gravity's pulling down with 5 newtons. The table has to do what? Push up with 5 newtons. 5 newtons down, 5 newtons up. Oh yeah, I'm going to ask that question again. How many people think the book is moving?
It's not.
How many people think the book is not moving?
I think it's.
It's amazing.
It's not a baby. Books don't move. They sit on tables.
What happened? I said,
I clearly said,
But how do you know what was moving before?
example, a book lying on a table,
You know it's lying on a table.
not moving. Unless you want to argue that the Earth is rotating around the sun.
Go to the table.
That's what you meant?
Yes, that is exactly.
And the Earth is rotating too, right? Okay. Now, there's actually a lot of people that I had one kid a couple years ago who said, because I used it for demonstration. He said, okay, so you're saying, Mr. Bennett, that the volleyball sits on the table and the table pushes up on the volleyball? Yeah.
Well, then how comes how it's moving? That's how it's.
How come what?
Because the ball's pushing down.
Because, now that's a good point. In this situation here, right, the first force is gravity down, right? The first force is gravity down, and that's on the ball, and the table is pushing on the ball up, right? So the forces are here. The forces are both on the ball. I can show you. If I push on the ball does what?
Squishes.
Squishes, right? Like I'm clearly applying a force on this side, and it squishes, right?
Yeah.
If I go like this, does the ball squish in the bottom?
Yeah.
Absolutely does. How?
Push it on top too.
Yeah, because I'm pushing on it. There's a force on the top, and there's a force on the
Bottom.
bottom.
Wouldn't that mean if you took out gravity, the ball would just float up?
No, because it would just sit there, right? I think it would just hover.
But so what happens to that opposite force? Does that only come with gravity?
Equal and opposite, right? So if I push on the table with 50, the table has to push up on 50, right?
Oh.
Gravity's pulling down. If it's not pulling down, then the ball's not pushing on the table, so the table says, "Oh, hey, I ain't pushing on you, man." That is. Oh no, there's one more. One more slide. What could it be? Oh, I never showed this to the morning class.
So you did get farther.
We went